So now let's talk about the acidic buffer. We have seen some basic definition of buffer solution. Now what is a acidic buffer? What is an acidic buffer? Acidic buffer is actually weak acid and its conjugate strong, a salt with strong conjugate base. So that is called the buffer solution. Let's say we have CH3CO acetic acid and CH3COONA. So whenever in elementary problems you will be given directly acetic acid and sodium acetate. So let's say it is C1 concentration and it is C2 concentration. Both should be present in the solution. When we have B solution, it is CH3COOH plus NaOH. Both is forming CH3COONA plus H2O. Here we have, let's say, molarity is M1 and volume is V1. Here molarity M2, volume is V2. Now when both has been reacted and NaOH must be limiting reagent. So when it is directly given means directly given that it is a buffer solution. But when we don't want to give it directly or it want to trick the question, then it must be given you that we have an acetic acid molarity volume and sodium hydroxide is put over it and molarity and volume is given, and we have put in limited amount of sodium hydroxide, or we can say sodium hydroxide is a limiting reagent. So here it will form M1V1 minus M2V2 and it will form M2V2. So in the solution we have acetic acid. We have acetic acid plus sodium acetate. This is M1V1 minus M2V2 divided by V1 plus V2 and it will form M2V2. Here it is M2V2 upon V1 plus V2. So here it is acetic acid and sodium acetate is formed. Now let's say we have acetic acid CH3COO sodium acetate and we are reacting with HCl. It is forming CH3COOH plus NaCl. So again it is one more trick it could be given. You have sodium acetate and you have dissolved H plus. So it is salt of weak acid and strong base and you have added strong acid which is in limiting reagent. Here it is forming the CH3COOH plus CH3COONA. Both these remain in the final solution. So there are two methods. By indirectly we can form the salt. Form the basic acidic buffer. We can form the acidic buffer. One, a salt of weak acid and strong base and we add a limiting amount of strong acid. And one case that we have seen previously. So now let's try to find out the pH of a buffer solution. What could be the pH of the buffer solution? So let's take an example. We have acetic acid and sodium acetate. We have acetic acid. It form CH3COO negative plus H positive and sodium acetate CH3COONA forming CH3COO minus plus Na plus. So actually Ka, if we write it for Ka is CH3COO minus into H plus over the CH3COOH. The sodium, the formate ion, the acetate ion over the acetic acid. Now the concentration of H plus comes out to be Ka into CH3COOH upon CH3COO negative. So that is the H plus. And all the this coming from salt. We know when we have a weak electrolyte and we have a strong electrolyte, all the ion we consider from a strong part only, that we have seen already. So if we take negative log of the both side, log H plus is to log Ka plus log of salt upon acid. So here it comes out to be pH. pKa plus log salt upon acid. pH equals to pKa plus log salt upon acid. So that's how we can calculate the plus log. Actually, it is negative log of salt upon acid. H plus equals to negative log of salt upon acid. And here pH equals to pKa plus log salt upon acid. And this particular equation is known as Henderson-Hasselbalch equation. And this equation is calculating the pH of a buffer solution. So it is applicable when 1/10 is less than salt upon acid concentration and it is greater than 10. So it is Henderson and Hasselbalch equation is there. So that there how we do calculate the pH of a solution. 1/10 concentration of salt upon acid into 10. That is called a Henderson and Hasselbalch equation. Now, why it is important? Because acid and salt concentration should not be allowed. Like we have that much amount of acid and we have put it that much amount of salt, or we have that much amount of salt, we have put it that much amount of acid. The ratio should not be vary from 1/10 is to 10 is to 1. Now here there is a problem. Calculate pH of a solution containing. We have directly given acetic acid and sodium acetate concentration. K is given. Simply pH equals to pKa plus log salt upon acid. So what is pKa? pKa is 5 plus log salt concentration is 0.2 and acid concentration is 0.1. 5 plus log 2. So it is 5.3. So here one more problem. pH of a solution obtained by mixing. Now here given acetic acid, formic acid and calcium hydroxide. So let's react both of them. We have formic acid HCOOH and calcium hydroxide. So we have HCOO whole twice Ca plus 2H2O. So here we have the concentration of formic acid is like we have 200 ml. Let's change the data. We have 200 ml. Now I'll again encourage you pause the video and try to answer here by your own. So we have 20 ml here and we have 5 ml. So it will form 1 mole of calcium hydroxide required 2 mole of acetic acid. So actually and we will be using stoichiometric coefficient 2. So 20 minus 10 equals to 10. And it will end over here and it will form 5. So pH 4 plus log pH equals to pKa plus log salt upon acid. So salt is like now how much salt is formed? Calcium hydroxide gives Ca plus 2 and it will give the Ca plus 2 and it will form 2 moles of CH3, 2 moles of formate ion, HCOO negative ion. So it will 1 mole of calcium this calcium formate will given 2 mole of this. So it will form 5 into 2 over the 10. So it pH comes out to be 4. So pH of the solution is 4. Remember when there is polybasic acid or polybasic acid, polyacidic base. In this case we have acidic base. So here we have to remember that the concentration on the derivation we have used was HCOO minus concentration which was came from salt. Now let's talk about the buffer range. What is the range of the buffer? Up to what range the buffer is active? So we have seen the concentration of salt upon acid when it is 1/10. So acid is so it is pH minimum pKa plus log 1/10. So it is pKa minus 1. When we have a salt upon acid equals to 10/1. So pH maximum comes out to be pKa plus log 10 by 1. So it is pKa plus 1. So the buffer range is pKa minus 1 to pKa plus 1. So this is the range of the pH of buffer. Now when the buffer is most means best buffer, so we could write when the buffer is best. So when the buffer solution is best, so buffer solution whose resistance for the change in pH is maximum. So resistance change is maximum, that is salt upon acid should be 1. So pH equals to pKa. So its change in the resistance is 1, or means maximum. So it will maximize the resistance change of the pH. So now we're going to talk about the buffer action, as I told you already. How does the buffer work? How does the buffer work? So let's talk about the action of the buffer. How does the buffer work? So we have sodium acetate. It is a strong electrolyte. It will form acetic ion and NaOH. And we have CH3COOH, which will form CH3COO minus plus H plus. We have both in the container. Now you added some amount of H plus and some amount of OH minus. And as we have keep on observing that the concentration is not changing. Now how it is not changing? How it is not changing? So whenever you are adding H plus, we have a numerous amount of acetate ion, and we will be considering it from this part only. So when in acetate ion we have add H plus, it will form CH3COOH reversibly. So actually K of this reaction is actually 1 by Ka, right? Which is very greater than 1, because K is very less. So all the H plus will convert into acetic acid. So the impact of H plus over the solution has been diminished a lot. Okay. Now we are adding this, let's say it is A case. Now we are adding base B case. Now we are adding B. So what will happen now? When we are adding the OH negative in the solution, it will react the acid. So we have acetic acid. So OH minus will react with CH3COOH. OH minus will react with this, and it will form CH3COO minus plus H2O. And will form CH3CO minus H2. So there is a thing to observe here, that it is a strong base and it is converting into weak base. So strong base has been converted all into a weak base. So nothing will happen. There was a lot of negligible change over here. Now let's say when we have added the strong acid and we have added the strong base. We have added a strong acid and we have added a strong base, then what will happen? The pH of a buffer solution. So first of all, a strong acid is added. When we have added a strong acid, so strong acid will react the salt. Let's say a millimole of HCl is added. It is CH3COONA plus HCl. A millimole of HCl. And then forming CH3COOH plus NaCl. HCl, it will form CaCOH plus NaCl. Its concentration is C2, its concentration is C1, and its the millimoles we have added is A. Now it will be C2 minus A, and it will form and this will form C1 plus A. So pH comes out to be pKa plus log C2 minus A upon C1 plus A. So pH will reduce. When we have added strong base, let's say strong base is added. So let's B millimole is added. So it is CH3COOH plus NaOH, and we have added CH3COONA plus H2O. It is C1, it is C2, and it is B. So it will form C1 minus B, and it will form C2 plus B. Now base will react with the acid. So again the pH will increase. pH equals to pKa plus log C2 plus B upon C1 minus B. So pH of the solution will increase. So that will happen when? So first of all, if C1 equals to B, when C1 equals to B, then it will be a case of it will form CH3COO and it will be the case of salt hydrolysis. Not all the case of B will. It depends how much amount of base we have added. In a strong base, not in the case of acid, it is applicable only on strong base. If B greater than C2, so it is NaOH and CH3COONA. So we have added NaOH. Now the NaOH will be remain in excess. So it will be simply the case of strong base. Now in the third part, if B is less than C2, so now we have this acetic acid and CH3COONA. So that will be acidic buffer, and the case we have seen over here is the exactly case where C2 and C2 moment. Here we are talking about C1. Here all we are talking about C1, nothing to do with C2. So when B is greater than C2, C1, so that will be the case, and B is less than C1. So this will be the case of acidic buffer. Now there is a problem. Let's first understand the problem, then try to solve it by your own. Let's see, we have a 12 gram of acetic acid and 16.4 gram of sodium acetate in 1 liter of water. We have given the volume of also the water, and Ka we have given already. So we have to calculate the pH. So first of all, acetic acid and sodium acetate, yes, they both combine to form a buffer solution, and specifically it is acidic buffer. Now we have added HCl, some amount of HCl, and we have increased the amount of HCl. Now finally we have added some amount of NaOH. Now we have to calculate the change in the pH of the solution. So let's start the problem. The moles of additive, the moles of added acetic acid, the moles of acetic acid is 12 over the 60. 12 gram is given, so it is 0.2 mole. Now moles of salt strong, the moles of salt is 16.4, and the molar mass of CH3COONA is 82, that is 0.2. So first of all, pH equals to pKa plus log salt upon acid. So pKa is what? 5 plus log. Salt is 0.2 upon acid is 0.2. So salt upon acid, it will become 5. Now we know the volume will be same to both of them. So volume will be cancelling out. Now let's say we have added 3.65 gram of HCl to it. So HCl will not be reacting with acetic acid. Obviously HCl will react with the salt part. CH3CONA is being reacted with HCl and it will forming CH3COOH plus NaCl. So it is 0.2 and 3.65 gram means 0.1. So it will form 0.1 and it will form 0.1. So actually acetic acid was initially 0.2, right? If we see initial T equals to 0, we have calculated both was a 0.2. If we see over here, acetic acid and salt, both are 0.2 molar. Now it will become 0.1 plus 0.2, it will be 0.3. So pH equals to pKa plus log salt 0.1 upon acid 0.3. 4.52. So change in pH equals to 0.48. Third part. We have added 7.3 gram. So it is 0.2 gram, it is 0.2 gram and it was also 0.2 gram. Actually 7.3 gram means upon 3.65, that is 2 moles. 0.2 moles. So it will be 0.2 moles. It will end over here, it is 0.2 plus 0.2. It will become 0.4. So it is purely a acid. It is acetic acid, which is 0.4 molar. Now we calculate the pH of a weak acid. We calculate Ka over the C. K is 10 to the power minus 5. C is 0.4. So it is coming out to be 2.5 into 10 to the power minus 5. Which is, which can, means 1 mile alpha could be neglected by alpha. So we can go by traditional method, or we can say conventional, easier method, where we neglect and H plus equals to K into C. So K is 10 to the power minus 5 and C is 0.4. So it is 2 into 10 to the power minus 3. So pH comes out to be 3 minus log 2, that is 2.7. Now in the third part, again in third part we have acetic acid. We have acetic acid CH3. We have like acetic acid means Na plus HCl, it is forming CH3COOH plus NaCl. It is 0.2. HCl we have added 0.3 and it is 0.2. So it will completely totally will end in, it will form 0.1 and will form 0.4. So pH. Now what is in the solution? We have HCl and we have acid. Now we know when we have a weak acid and a strong this is weak acid and a strong acid, all the H plus we will consider from a strong acid. So moles of H plus, molarity of H plus, concentration moles over the volume 1 atom. So pH comes out to be 1. Now in final case we have added some amount of NaOH. We have acetic acid that will be reacting with NaOH and it will form sodium acetate plus H2O. So here acetic acid is 0.2 molar, NaOH is 0.1 molar and sodium acetate 0.2 molar. So it will be 0.1, it will be added and it will be 0.3. So pH comes out to be 5 plus log of 0.3 over 0.1. So the pH will become out to 5.48. So pH eventually increases on adding the base, obviously, in the buffer solution. Now we can also see how we have added acid and base in the buffer solution, how the pH has increased or decreased on adding acid and base.